I hope you have brought your fresh minds to this session. All right, folks, welcome everyone. Today we are going to talk about quite a few topics. Today will also represent a transition from covering the very basics of machine learning, some of the concepts that we are doing will transition us from things that are broadly about machine learning itself to things that are specific to neural networks. Before I do that, any questions about what we did the last time? Anybody? All right. So I'll give the plan for today. We are going to cover the following topics. Now, if you're wondering why I have a black board today instead of a whiteboard, it is primarily to reduce glare for people who are physically present here.
So the screen is not being shared.
Oh, the screen is not being shared. I apologize. So let me take care of that. Am I screen sharing now?
Yeah.
Okay. All right, folks. So there are three main topics as our lesson plan. We are going to do a bit of loss function. We have implicitly been talking about it. We said that you take the loss as a measure of departure of predictions from reality. But it has to be a differentiable function. Then we can take its gradient. If we can take its gradient, we can do backpropagation. Today, I'll touch upon the common loss functions that occur in deep learning quite a bit. And then we'll talk a little bit about optimizers. I won't talk too much, but because we have talked about it. This is one of those topics which, in the interest of time, I will leave it as a self-reading for you. It is very well explained in the textbooks. It's not something that necessarily needs a lot of explanation, but I will briefly touch upon this point. We will do this. And then, along with the loss functions, when I'm explaining, I'll explain things like cross entropy, negative log likelihood, etc. A few of these basic ones I'll talk about. And then finally, the big topic of our day is convolutions. Convolutional. Quite a big word, convolutional neural networks. It's probably the only time I'll use the entire word. Usually people use the acronym CNN. So that is our plan for the day. So today we won't get that much time to do the lab part of it or to show examples, but in the end, I would like to walk through some examples, time permitting. For that reason, ask your questions judiciously. Like if you feel it can wait till the very end, and then wait. If you feel it's very pertinent to what we are talking, or it will help you understand what we are talking about, then of course, do please ask the questions. So we talk about loss function. Let's go to the first topic, loss function. This is also variously called objective function. Some people use it. Objective function. People also call, and it's represented with all sorts of notations. But I will use some very simple notation to do that, and not quite accurately, but one part of it is error function. Error function. So I'll illustrate this with an example. Suppose you have let's say you have a function and you have some data. Let's say that the data is like this. So if you draw a hypothesis, like let's say that your hypothesis or the function, the model that you built is something like this. A very simple model that goes like this, a straight line through the data. I'll take an example. And you build another model, which let us say is like this. Now, between the blue model and the orange model, which of the two models would we say is a better fit to the data, is a better modeling of reality? The orange one. But mathematically, how would you say that? Like looking at it, what would you say?
The error is less.
But what is the error? Y hat minus y. Or now let me, while we have been saying it like that, let me put it in a more geometric way. Which of these surfaces, now even though we are seeing a line, a curve, I'll generalize it to the concept of a surface. And so bear with me because I want to introduce notation or language that I tend to use quite a bit and that later on will come in. So a line generalizes to curve, some curve, right? In higher dimension, line generalizes to a curved surface or a hypersurface. And much more specifically, if your surface is smooth, right, which is one of the things we want in machine learning, we always try to approximate things, or it's a desirable to approximate things with smooth differentiable smooth curves. Are we together? So when we do that, you can say that if you add smoothness to it, plus smoothness, the mathematical concept, roughly speaking, becomes a manifold. These things are called manifold. A manifold, right? So let me dwell a little bit about the manifold concept. What is a manifold? See, imagine that you started out with a clean sheet in your bedroom, right? Then you got into bed, you went to sleep. It's a flat sheet. But once you get into bed, what happens to that sheet? You get between the sheets, the sheet that is covering you, that you put on top of you, or the blanket that's covering you, it goes from being flat to getting crumpled up, isn't it? But while it crumples, what would happen to a little ant? Imagine you have a little ant walking on the surface, right? Or a little bedbug that's walking on the surface. When the sheet is flat, the ant sees locally, what does the ant see? A flat surface, right? Or a plane. The ant sees a plane, isn't it? Are we together? And the ant, when it walks straight, it is the same as a straight line. But what happens when the surface gets crumpled?
It's a noise.
When the same ant walks, does the ant know that it is upon a crumpled surface? It's a very tiny ant. Locally, in the vicinity of that ant, what does the surface still look like? Flat, right? If it is a really tiny ant, if it is a little dust mite, to it, the world still looks flat locally. but you can see that it's crumpled, isn't it? So what you say is, and this is a quality of a manifold, you say manifold is any hypersurface. And this is a, by the way, the formal definition of a manifold is a little bit more complicated. There are there's things like Hausdorff compactness, etc., etc. We won't get into, but geometrically, intuitively, it is any hypersurface that locally feels flat. Let's stick to this more intuitive word. Right? That if you're really tiny, it will feel flat. And the other property of a manifold is that this local is called a map, a little patch. The word for that is map. Right? So, for example, this ant may have its local. Suppose that insect just lives in that neighborhood, so it may make its own map. This is my north. This is my south. This is where I go, and so on and so forth. But the whole surface is an atlas as a collection of maps or patches that each look flat. The technical word people use is Euclidean, right? The notion of distances are preserved. Euclidean distances are preserved. So these things are called manifolds, right? So now let me give you another interpretation of this. Would you say that the better model, the orange, is much more proximal to the data than the blue model? Right? Geometrically, it is much more proximal to it. So this is a question of regression. We are trying to predict certain values, and this proximity of a manifold to the data is a very good way of thinking about loss surfaces. We'll talk about it in a little moment, but let's take this question of regression itself. So what happens is that if it is, let's say that at this point, I will take this point referentially. Let's take this point. This point is much further from the blue line than it is from the yellow line, yellow curve, isn't it? And so one intuitive way that you can quantify how close a surface is to data is to just look at the gap between the point and the surface that corresponds to the same value of x. Right? Given xi, this real value is, of course, and now if you think in terms of what this real is, this is the reality. This is the y hat of the blue model, and this point is the y hat of the orange model. Right? So if you look at it, what we are seeing in a very intuitive sense is that yi minus yi hat, or the other way around, it doesn't matter, is sort of for orange is less than yi minus yi hat, the magnitude of it. Let's look at the magnitude for the blue. Is that what we are saying? But you know, this may not always be true. For example, you may look at this point. Let's look at this point. For this point, let me call this point J. So this maps to xj. For the jth point, you would agree that the blue line seems to be doing better, isn't it? So based on which point you pick, one model or the other seems to be doing better. Would you agree that in this particular case, yi minus yj minus yj hat of orange is actually greater than yj minus yj hat for the blue hypothesis? The blue hypothesis seems to be doing better. So why would we have taken 2 points, one favors the orange, one favors the blue. So what is a tiebreaker? How do we decide that no, we prefer the orange model more, the orange hypothesis much more? What makes you feel so?
Number of such summation, right?
Right. What you say that on average, intuitively we say, hey, that is just 1 point. But when you look the overall, the cumulative effect, you're looking at intuitively what you're saying that the cumulatively orange hypothesis is closer, orange manifold or hypothesis. And do you realize, guys, that I'm using the two words interchangeably? What you think of as model or a hypothesis is geometrically nothing but the manifold. So much of machine learning is actually the search for the embedding manifold that's most proximate to the data, or that's somehow very significant for the data. In the case of classification, you'll see that it becomes is that manifold that best separates the classes. And so we'll come to that. Is closer, but let's stick to regression problem. This is a regression where we are trying to model this. Hypothesis is closer than the blue manifold. That part is obvious. Now the question is, how do we define cumulative? We do know that we can't take, why did we take the absolute value? Anyone? Because the value could be negative or positive, isn't it? Right? It doesn't matter whether you're above the hypothesis or below the hypothesis. What matters is what is the gap between the hypothesis prediction and the reality, isn't it? So you know that you need to do, let's define a quantity error. Epsilon I for a point is y minus yi hat, right? And any kind of a cumulative that you do, you can't do a cumulative. You cannot do this, because if you do this, you run the risk of not actually accumulating what you want to accumulate. What you really want to accumulate is this, isn't it, guys? Now, there's a problem with this. You say, okay, the absolute value. But when I look at absolute value, here comes an interesting thought. I can take the absolute value to any power d, and it would still serve the purpose. Do you see that, guys? I could take absolute distance. I could take squared distance, isn't it? And I could take cube distance. I can take a fractional distance. I can do anything. In fact, when you define the distance like this, right? And when you write this distance like this, there is I'm just introducing a bit of words that if you don't remember, that's all right. The mathematician who first realized that so long as we take the absolute value, you can compute the distance as absolute value to any power, fractional power, integer power, squared power, whatever it is, 1/2, 1, whatever it is. That mathematician was called named Minkowski. And so in his honor, we speak of Minkowski distance. The Minkowski distance between 2 points, we define therefore 2 vectors, therefore, and points are vectors, is in any dimension space, doesn't matter. It is always, let's say that I'm using the yi between 2 points. So the strict mathematical definition is distance d between point x and x prime is basically, let's say that x is made up of vector x1 to x, it's an n-dimensional vector, belongs to n dimensions. And likewise, x prime would be a vector x1 prime all the way to xn prime, right? So I hope I'm talking common sense here. Then the distance, that Minkowski distance, d x prime, is defined as literally x1 minus x1 prime, absolute value, to the power d. Do you see this? To the power d plus x2 minus x2 prime to the power d, and so on and so forth, to xn minus xn prime to the power d, and the whole thing to the 1 over dth power. This is called the dth norm, and people often call it the dth or dth norm. More strictly speaking, dth Minkowski distance. So now see, let's see what it does it mean. For d is equal to 2, what does it look like? It just becomes d2 x prime, just becomes the Euclidean distance, isn't it? Suppose you're doing this. This is nothing but your Euclidean distance square root, the classic Euclidean distance, right? What does it mean? Let's look in 2 dimensions. In 2 dimensions, if this point is x and this point is x prime, what is the Euclidean distance between the two? It is distance as the bird flies, isn't it? Are we together? Right? But it turns out that while birds have that privilege, if you live in a city, for example, like Manhattan, you can't fly like a bird. Like when you take a taxi, and let's say that you are here and you want to go here, and the whole city is on a grid. As you know, many cities are on a grid in the United States, things like that. And these are the streets there, let's say. Let's make the streets a little bit more like this. Huh? These are your streets. And suppose you want to go from X to X prime location. You get into a taxi in Manhattan. Do you think the taxi can will compute the distance as the bird flies? What will the taxi do? The taxi will have to take any one of these paths. It can go like this and go like this. That is path 1. It can go like this and this, or it can go like this, or it could go, I don't know, it can take any one of the variations. For example, it can go like this. Any way it goes, the cumulative effect is it would have gone x minus x prime, absolute value. You know, it would have gone, what is the distance from here to here? X prime minus x. Let me write it the other way around, because in this case, x prime seems to have the greater. Would you agree that this is the value? And how much is this distance? This is x1 prime. This is x1 prime, and this is x2 minus x2. So this is the x1 axis, and this is the x2 axis. So this is x2 prime, right? X2 prime minus x2, right? This is what you would have gone. And by the way, how would you account for going back from, like if you were going to a point x prime prime, this is negative value, then you would realize that you just need to take the norm of the distance. What matters is not whether you're going backward or forward, but it matters how much you are going. Does that make sense? And so for the Manhattan taxi driver, Manhattan driver distance by which he'll charge you for the ride would be, that is the d1 x prime would be x1 minus x1 prime to the power 1 plus x2 minus x2 prime to the power 1, and the whole thing to the power 1. So this is what? This is the Minkowski norm of, what is the Minkowski norm here? N is equal to, norm is equal to 1, right? Are we together, guys? And so each of these, there is a certain intuition that you can apply to these norms. Right? This is often called the Manhattan distance. We'll exploit this fact later on when we do regularization one of these days. But I hope the concept of distance you're getting. Go ahead.
So in Manhattan distance, the D is 1, but in Euclidean distance, D is 2.
2, exactly.
That is the difference.
That's the only difference. And now we can generalize from that. So think about it this way. What is a circle? Let's go back to our grid. Circle, can we define a circle to be the set of all points which are a unit circle? A unit circle is a set of all points that is at unit distance from the center, right? Let us say that the unit distance is this much. This is half the distance and this is 1. So it would be what? It would look like this in Euclidean space. It would look like this, isn't it? Oh, what would a Manhattan distance look like? It turns out you can go 1 unit this way, you could go 1 unit this way. So these 2 points are preserved, but you could go half a unit here and half a unit here. So this point is also at 1 unit distance, isn't it? Look at this point C. It is also Manhattan, 1 unit Manhattan distance away. And so you can convince yourself that the Manhattan distance, a circle in the eyes of a taxi driver, is this. He says this is the circle. Every point here is at unit distance as far as I'm concerned. Are we together? And so this is for D is equal to 1. This is D is equal to 2. And then you can convince yourself that if you keep on doing D is equal to half, which is a little bit harder to visualize, will start becoming pointy. You notice that D is equal to half. Now, D is equal to 1 already looked like a diamond. It had a pointy edge, right? It had a corner to it. It wasn't smooth. D is equal to half really begins to look like a really pointy sword, like the tip can pierce something. And that fact is essential when we talk of regularization and dimensionality reduction in machine learning, but we won't go there. And the converse is also true. At the end of it, if you start going to higher and higher Ds, it will begin to approximate this outer square, but we won't go there. D is equal to 3, D is equal to 4. And mathematicians take quite a bit of liberty. They can go to D is equal to infinity, right? In which case, you can convince yourself that you'll begin to look like this. So we won't go there. I just took a digression because I wanted to touch on something that we'll need in regularization while I was talking about distance. But invariant of what your notion of distance is, you agree that I can compute. When it comes to these points, I can accumulate all these distances here. Going back to, coming back from our digression, we can accumulate, cumulatively, we can go and do some level of distance. Now, those introduce various simple loss measures. If D is equal to 1, you call it the maximum, and so, see, here's the thing, you have n points. So if you are creating a loss, quite often, to normalize it, you divide it by the number of data points. That makes sense? So that if you double the number of data points, it doesn't mean that your loss doubles. You scale it down by the number. So this is called, so you take the mean. 1 over n takes the mean, isn't it? So D is equal to 1 is called mean absolute error. Now let's deconstruct this word error. This is you're adding up the errors and dividing by n. That is true, and you're taking their absolute value, because if you don't take the absolute value, it wouldn't make sense, right? Are we making sense, guys? Right? So that is the MAE loss, mean absolute error loss function for regression, right? When you're trying to fit a manifold to data points and use that to predict numbers, the next value. The mean squared error loss is D is equal to 1, because then what are you doing? you're doing yi minus yi hat square summation. Then you can forget about the absolute value because that is implicit. If you take even a positive or negative number, it will square itself. So would you agree that this is also a possibility? And you can go further. Usually people don't go to higher terms. Now the question arises.
D equal to 2 or D?
Oh, I'm sorry. Yeah, thank you for correcting me. D is equal to 2. Euclidean, right? So remember that the MSE laws, mean squared laws, takes the Euclidean errors, whereas MAE just is looking at the absolute errors. Now, which of the two should you prefer? And how do you decide? It turns out that this problem was puzzled over by people when the MSE laws was historically the person who we today know was one of the first to, or perhaps the first to formulate it, was the mathematician Gauss. And he used it in his paper in, when was it? 1793. Right? But he was rather particular. He didn't reveal his secret. Right? And then Legendre wrote a paper in 1805, which he called the method of least squares. You see that what is the point of least loss? When this loss function is minimum, that's what you search for, right? Least squares. And that was in 1805. And the moment he published the paper, historically, Gauss jumped up from his seat and says, "No, wait a minute. I did it first." And it led to one of the most entertaining, what in our community we call the prior debate. Who did it first? And science is filled with this entertaining prior debate. So, as you know, some people say Marconi discovered the radio. But then some people say, no, it was J.C. Bose or somebody like that, right? And then after a lot of debate and prior investigation, now it turns out that the idea occurred to a host of people more or less simultaneously. So this is part of the entertainment people have in our fields, in the mathematical fields. Who got it first? Right? The prior debate. So we now know Gauss did it. So, but then came around 1812, I believe, came an important theorem, and I'll mention it today. It is often called the blue theorem. That is how I've seen it referred to in the US in some of the econometrics books. But mathematicians just call it the Gauss-Markov theorem. And I believe the date is approximately 1812, pretty close. So within a few years, they had figured out that the best thing to do is to take the squares for loss under certain well-behaved conditions. And that is important. If your data doesn't have extreme outliers, right? So it should not have not big outliers. If it shows a statistical property called homoscedasticity. Now, I hope this looks suitably frightening, this word, if you haven't encountered it. Right? So what it basically means is that the departures, right, from the hypothesis, if you square the variances, they don't blow up. They show more or less a uniform variation across the spectrum of the input, across the spectrum of the values, right, of the y values. So homoscedasticity. So there are certain well-behaved properties. I won't go into the statistical properties, but under those conditions, the Gauss-Markov theorem says that squaring is a good idea, which is why for regression problem, and in fact, for most of the time, when you're trying to fit your data to a regression problem, you invariably end up picking up the MSE loss. You must have noticed that in our homework, PyTorch homework, what was the loss function we took? We literally took the MSE loss function by default. But when there are significant outliers, then what happens is that you realize that error, which is yi minus yi hat, this term, the outliers will be far off from your hypothesis, and they will exert an undue influence on your loss function, isn't it? They'll blow up. And so when you do gradient descent, you'll realize that those outlier points, they are sort of hijacking the whole learning process a little bit, isn't it? They're becoming loud voices that have extraordinary influence. So under those circumstances, you would realize that it would be much better to take just the absolute value, because then the outlier or the things that are far off are not blowing up. Are we together? So, those are the considerations. Now, there's quite a bit of literature on what to do, what not to do, and so on and so forth. But I want to give you an intuition about why this theorem sort of holds by giving somewhat of a cheesy analogy.
So,
So-
how do you recognize that?
The presence of outliers? Oh, we have outlier detection algorithms. So we won't go there because this course we focus on deep learning, but there are outlier detection algorithms.
So, how do you, I guess, is there a problem when the loss is close to zero? Like, that's what they call overfitting the data.
But no, that's a separate problem. Irrespective of which loss function you take, if your model is extraordinarily complex, it will overfit the data. In standard thing. Well, and I must add the caveat that with neural networks, things get a little bit more weird. It has a problem of double descent, etc., etc. I've talked about that. We won't go there, but let's stay with the code, with the loss function itself. I'll give you one intuition of why Gauss-Markov theorem or BLUE theorem. Oh, by the way, what does the BLUE stand for? Where did they come up with the word? It stands for best linear unbiased estimator. What it says is that when you're trying to fit a straight line or a hyperplane to the data, then under certain circumstances, this is the best linear unbiased estimator. Unbiased means whatever model you build for a sample of the data will hold for the whole data. The word unbiased in statistics has that specific meaning. Right? So we won't go there, but I'll give you one intuition on why this works. See, when you have little kids, if you're a school teacher or if you're a parent, one of the habits that you learn in good parenting is that when people make small mistakes, and you turn the other way around, you don't notice it when kids make small mistakes. You turn the other way around. You don't pounce on your kid when they're making tiny mistakes. Right? They're a little bit of mischief in the house. It's part of fun and frolic. But if they do something egregiously wrong, you pounce on them. Right? And that becomes a teachable moment. And if you think about it, when you take the square of an error, it does exactly that. It amplifies the big errors and makes you pay attention to it. It becomes a teachable moment for the model, but small errors sort of wash out compared to the big ones. Okay. So it's sort of an intuition you can carry with why squaring is so far more popular than this. But that's not the whole story. Obviously, if you look at the literature, there are many, many loss functions for regression, like Huber loss, for example. Huber loss, what it does is, it says, why don't we take the best of both the worlds? For points that are non-outliers, Huber loss, it basically for non-outliers, like beyond, like whose distance is less than certain, where the y minus y hat error is less than a threshold, then just use Euclidean loss, error square, right? Square the term, error I. But if it is greater than that, then do absolute value of the error. And I think you subtract also a delta minus 2 or something like that. There's something, but the basic idea is you switch from one to the other based on how far the point is from that. So Huber loss. And if you look at the literature of regression loss functions, there is a vast and long literature, right? People have spent quite some time. So that is the story for regression. Now, let's take
one quick question. So the manifold,
Mhm.
the word smoothness,
Mhm.
what is the intuition there? What are you referring to when you say smoothness?
Smoothness means differentiable. Right? So the word smooth, any curve will be smooth at this point if and only if it will have a derivative. If the dy, let's say that you have x and y, if dy dx exists, if it exists, it is smooth. But this is not smooth because here, non-differentiable point. You can't take a derivative here.
And how does that apply to the manifold diagram?
Simply, see, the thing is, the moment you realize that derivatives, they measure the rate of sensitivity to small. So at points that are pointy, that are non-smooth, the response is very sensitive to the input, isn't it? So a manifold is just a surface on which you have very small gradations, smooth gradations, right? So for example, this is a manifold. This is not a manifold. So what is a name mathematicians give for that? They may call it, because it's continuous, they may call it an orbifold or something like that, but it's not a manifold.
And so in the diagram above, which you have drawn there, it will be right there.
Oh, no, no. This is about distance. This is just the distance thing. It has nothing to do with the surface. This is just measuring the distance. So, but if you look at this diagram, look at this diagram. So, do you notice that both of these surfaces that I drew are smooth surfaces? Right, smooth. So you always try to approximate or build models that are manifolds. That's a very good thing to do. You don't always do it with neural networks. You do. For example, if you do random forest or decision trees, then the decision boundaries or the models, yeah, they have step. They're decidedly not manifolds, but neural networks they are. Yeah. So now, what about classification? The other class of problems that we try to solve in classification. So suppose I have blueberries. Blueberries are tiny. Let's say that my axes are weight and size. So blueberries are tiny little things, right? And let's say these are your blueberries. These are the points for your blueberries. And then you have strawberries. Right? Would you agree that your strawberries would look something like this? Big, heavy points. Like all the strawberries will be big and heavy. Does that make sense? On the weight and size axis. And so if you want to distinguish between a blueberry and a strawberry, what would you do? You need a decision boundary like this. Are we together? And you realize that the closer you come to the decision boundary, the less certain you are what it is. But the further away you go from the decision boundary in either direction, the more sure you are. Right? And so there's a whole set of theories for classifying. But the point that I'm trying to make is you have, once again, a manifold, which you call the decision boundary. For classification, that also is a manifold, right? It's a smooth surface that you search for with neural networks. With neural networks, huh? So I'm being specific to neural networks at this moment. It's generally true, unless you do decision trees and a very small set of random forests, etc. Most machine learning algorithms lead to smooth manifolds.
So
Now,
I had a question. I was
yeah,
like, is there any real world data which is inherently cannot be expressed as a manifold data? So if the data distribution itself is like steep,
oh
the
yes,
origin, what do we like? How does neural networks react to those kinds of things which cannot be
see,
normal?
suppose data, I'll give you an example. Suppose the data is like this. And you have the other points like this. So this is an example where I suppose this is what you mean, because the ground truth is, this is the actual separating plane, isn't it? It's pointy. Is that what you mean?
Yes.
So what the neural network will do is, it will nevertheless approximate it. It will approximate it as like this. Right? And this curve might get more and more bent. See, It may be very steep like this, but it will still be smooth. It will never be pointy. Are we together? Right? So remember that neural networks are approximators. So that's that.
Can you touch a little bit on the derivative as like, you know, a concept, just how that makes it smooth a little bit?
Okay. It's very simple. Think about it this way. I have a line. What is dy dx? 0. Right? I bend this line. Here the dy dx is in this region. Dy dx is greater than 0. In this region, dy dx is less than 0. I make it even more pointy, but still smooth. This condition still holds. But when does it break? So you realize that at the top, at the tip of it, I have dy dx is equal to 0 because it's transitioning from greater to 0 to less than 0. But what happens if I keep on making it pointy like that? So for example, if it is a bell curve, you keep on making it pointy, it begins to look like something called a delta function, right? It begins to develop a peak, very tiny. And in the complete limit, suppose it is here, can you even tell that there is a point where, like, there is no point? So suppose, like this meet, it meets like this. There is no derivative here, right? And do you notice that if you play along this analogy, what does it show? You're going from smooth to non-smooth. Does this make sense? And that's the intuition that things that are smooth will have a derivative. Things that are not smooth, the derivative will be indeterminate. You can't find the derivative. You have a sudden transition from going up very fast to going down very fast. Right? And another intuition that I'll give, which is not directly relevant, is
So the derivative indeterministic is equal to 0, right? That's what.
no, it is not 0. 0 is a value, it's a nice value. When you can't compute the derivative at all, that's when you lose smoothness. Yeah? The two things are what is geometrically loss of smoothness, algebraically is loss of derivative altogether, ability to take derivative. Right? So see what happens, guys, that all the problems, it's just a general statement, all problems in math, you can either look at it geometrically or you can look at it algebraically. If I say there exists a point at which derivative is indeterminate, cannot be computed, doesn't exist, it looks like very abstract. But if I just tell you that, see, we have this sheet of paper, everywhere you have a derivative, I bend it, there's derivative everywhere. But the moment I do this, I created a crease in the paper. Now tell me, is the derivative on the line of the crease, what is it? It doesn't exist, isn't it? So geometrically, it is so easy to see when you lose smoothness, isn't it, guys? You literally created a crease. So always think geometrically, it's much more intuitive. All right, so now let's think in terms of loss function for classifiers.
Sorry, staying there, the curve which you drew there,
Yeah.
the line between the blue and the irregular. So the curve there, where it is not a pointed thing, is it like an artifact of a neural network, or?
No, neural networks will never do that. Neural networks will always be smooth.
Yeah, that's what I'm saying. So the artifact of neural network architecture gives you the smoothness? Or?
Yes, neural network architecture inherently will give you relatively smooth, not always.
Yeah.
See, if you use ReLU, then you can see the patchwise combinations a little bit, but we still pretend it's smooth. Right? If you use a tanh or a sigmoid function, you'll always get smoothness, more or less. Right? So anyway, the point, where am I getting to? See, suppose we'll now come to a concept. Suppose you are classifying blueberries versus blueberry versus strawberry. Right. And now I'll come up with a concept. Suppose here is a fruit. Clearly looks like a strawberry. I should color it pink. Right? This is your strawberry. And suppose your machine comes up with a probability. So you pass this data into this machine and it comes up with a y hat. What do classifiers produce in neural networks? They produce a probability, right? Because of the softmax layer. Softmax or sigmoid layer at the very end. You remember that, right? So they'll produce a probability. Probability takes values from 0 to 1, right? Are we together? So y hat is probability. So more formally, we will say y hat, let's say, is the probability that it's a strawberry given the input data x. That's what it is, right? Y hat is the probability that it's a strawberry given the input data. From the input data, your machine says, hey, I think it's 90% sure it's a strawberry. That's what it will say, right? And probabilities take values in 0 to 1. So far, so good. Now the question is, let's try to create a loss function out of this. How do we do that? For regression, it was very easy. You just look at the gap, the distance. But here, the distances are hard to, there is no notion of what is the distance to a strawberry or distance to a blueberry, isn't it? So what do we do now? We have to do a slightly different exercise. Suppose you know that it is a strawberry. You ask the probability that it's a strawberry comes out to be. Let's take two situations. Situation A, the probability y hat, the machine comes out with 0.1. And situation B, y hat for a strawberry comes out to be 0.99. Now, which one is a better situation? B. You would trust your machine more if it was situation B. So we need to say somehow that the loss with the prediction B is much lower than the loss for the prediction A. Does that make sense? And now we need to find a way to connect the dots. So far, good? Let's try to connect the dots. First of all, you realize that, look at this. This is really bad surprise. Your model is not, you built a model and you got an unpleasant surprise, isn't it? This is not so surprise. Why? Because you know for sure that it's a strawberry. You have the ground truth, isn't it? You pass that ground truth, that strawberry through your machine. In situation A, it gave you a bad surprise. So one thing we could do, the intuition we get is, suppose we could measure the surprise. A good machine, a well-trained machine, will, if we know the ground truth, it won't surprise us much. Does that make sense? It will say things that the ground truth, align itself with the ground truth. That's what a good, well-trained model is. On the other hand, a poorly trained model will keep throwing surprises at us. It will make all sorts of bad guesses. So let's use surprise, somehow use surprise to quantify loss for classifiers. So how would we do that? Now observe one thing. When P is low, surprise is high. Remember this situation. When P is high, surprise is low. So we do see an inverse relationship, isn't it? So there are many ways to do that. One easy way you could say, what about, let's try a formula like 1 over P. Does 1 over P seem to align with our notion? Make it reciprocal, right? So when, so situation A, 1 over 0.1 is 10. Quite a bit of surprise, isn't it? And situation B, 0.99 is 1 point something, right? Approximately 1. I'll just leave it as 1. Is that fair? No, it will be 1.02, I believe, something like that. A little bit of a surprise. What about situation C? C, when it is, when the machine says with absolute confidence that it is a strawberry, right? Then this comes to 1. So you realize that, see, this formula seems to be a good candidate to measure surprises, isn't it? It does the job well, but there is a little bit, one tiny little wrinkle. When it makes perfect predictions, there should not be any surprise. It is still sitting at 1, right? So in other words, 1 over P, it belongs to the domain from 1 to infinity. Do you see that? It goes from 1 to infinity. Right? Is that clear?
Yeah.
Right. So, for example, if you take 1 over, if the machine said there is almost no chance at all that it is a strawberry, then this would go to infinity. Right. So it is that. So we are almost there, but it would be much nicer if surprise was 0 when the answer was correct, isn't it? So then there is a trick. Whenever you get in math a function like this, one easy trick is take the log of both the sides. What is the log of 1? Yeah. Now it will go from 0 to infinity, log 1 over P. Right? And let's say that this is the pth item, data item, or 1 over P. Are we together? Does this make sense? That this is the surprise. And now all works well. So this is our surprise that we got. And so now we have an end run, a home run. We can say the loss for classifier, one easy way is just to accumulate all the surprises, right? Which is the same as 1 over log 1 over yi hat. Remember the predictions. P and prediction is the same. Does that make sense? And so it becomes, well, now what is log over, what is this? This is, let's look at this term. This term is equal to, well, summation over I, you can forget about, log 1 minus log yi hat. What is log of 1? 0. And so this becomes negative log . Does this make sense? Right? This is it. Now you may say, well, you know what? You just did some hand-waving argument to come up with this loss function. So this is the famous negative log likelihood. Now you say, no, wait a minute. Where did the word likelihood come from? We were using probability, isn't it? So now why not say negative log probability? Where does the likelihood come from? And it turns out that what I made as a hand-waving argument, as an intuitive argument, has a much more rigorous basis. This result actually, and I won't go through the derivation, but actually I can go through the derivation. It comes from maximum likelihood estimator. What does it mean? Suppose you found that the first one was a strawberry. The second one was a blueberry. The third one was also a strawberry. Let me take 3 points. You realize that if your machine produces the probability 1 of strawberry, probability 2 of strawberry, probability 3 of strawberry, what do you want to maximize? You say, okay, it would be lovely if it said probability of strawberry and probability of blueberry. So what is the probability of blueberry? It would be 1 minus the probability of strawberry, isn't it? And 1 minus probability of P1, P2, P, right? Or let me just put it this way. It is the probability of blueberry, probability P2, blueberry, probability of strawberry for the third item. These are the probabilities. And a machine would be good if all of these quantities jointly were maximum, isn't it? So one way to look at it more formally is to say, I want to maximize, this thing is called likelihood. What is the likelihood is the joint probability of the entire reality, the ground truth that you see. A good model will make the reality very likely, right? So to make it very intuitive, if you go to Arizona and you make predictions of rain, a good model would be that makes most of the time says that, okay, it's not going to rain. And on the days it rains, it will say it will rain, which is the winter. Right? That sort of a thinking. So you want to maximize this. Now, maximizing very small quantities is hard because probabilities are decimals and numerically you get into trouble. So what people do is whenever you have to maximize quantities which are fractional, they say, you know what, let's maximize the log of, let me call this L, log L, because it's the same thing. Let's maximize the log of L, right? Because logs are still easy to compute numbers. It's just a numerical convenience. Albert, wait a minute. You can still compute log because log of 0.01 is just minus 2. Negative 2 is manageable number. But if you take 0.01 times 0.00001 times something, and before you know it, your machine is saying 0. Right? It gets numerically hard to compute. So people often take the log likelihood. And then log of this, right? What is the log of this? This would be, now log of this whole thing would be just log of probability, each of the probability P1 plus, basically, this is this plus log P2, etc., which is the same as summation over log Pi. Does this make sense, guys? Isn't it? It's the summation over the logs. And you say maximize this. Maximizing this, would you agree, is the same as, because most of the optimizers, numerical libraries in computer science and machine learning, they know how to minimize. So is the same as minimize negative log Pi, right? Or minimize this, which is the same as, or negative log L, L being the product of these numbers. Does this make sense, guys? Maximizing is the same as minimizing. What did we end up with? So this is again a good minimize. This is our loss function. This is our loss, right? Negative loss is, in this argument, loss is negative log L, which is the same as minus summation over log Pi, right? And so that is why this loss function is very important. So see, you can argue with it more formally with probability, and just a little bit more formally using called Emily, maximum likelihood estimator arguments, or you can look at it in a more intuitive way, the way I explained to you. Are we together? So for classification, you measure cumulative surprise, or when you average it out, average surprise, right? I don't know, somewhere in there you can throw in an average. But okay, this is what you're trying to measure with your data. Are we together, guys? Does it make sense now? And so that's all we'll talk about classifier law. So classification. And by the way, what is this quantity called? Log of 1 over p, negative log of 1 over p. Yeah, It is cross entropy. It is related to the concept of entropy. Right? Entropy is your measure of, think of it, entropy is your average surprise in some sense. Right? So classification law is, you often hear the word cross entropy, and they are related. For neural networks, they are very related. They're pretty much the same thing. Negative, log, likelihood. Do you see how these terms are pretty much saying the same thing? Right? And for regression loss, you have MSE, which is yi minus yi hat. And this is MSE square. And then you have MAE 1 over n at this. Then you have Huber, MAPE. I'll let you figure out. There are lots of them, Huber, MAPE. And for classification also, you can create many, many variants of this. So this is about loss function. See, throughout we have been talking that somehow you can quantify how much mistakes you make and then be able to take the gradient of the loss and back propagate it. We have been saying this all over. But what I didn't cover was how exactly is this loss measured specifically. Right? So I hope now we covered that. Let's recap what we said. For regression problem, intuitively, it is to what extent the manifold departs from the actual points, it strays away from the actual points, data points. That's your loss, intuition version of it. Whereas intuitively, classifier loss is to what extent the predictions are surprising you unpleasantly. Right? The net surprise or jolt that you get, oops, my model doesn't work. That's your loss. Intuitively, is it making sense? But then you can, with classifier, you can actually ask a tricky question. You can say, hey, let's look at this one fact. And this is only for, if you happen to notice, you say that, see, suppose the probability of something is y hat is some probability, right? Y hat, which is p hat, is equal to 0.8. Why don't I, you know that if something happened, it was a strawberry, why don't I do this? Square it. This also may do, right? So people have asked this question. Think about it this way. This also may serve the purpose. You may say that if the probability is 0.1 of something, then 0.1 minus 0.1 square would be 0.9 square. Just like mean squared loss. But if something's probability is 0.99, 1 minus 0.99 square would be approximately equal to 0. Why did we not use that? After the squaring was such a nice business when it came to regression. Now I'm arguing against myself and saying, why didn't you use such a simple formula? Why did you have to do the reciprocal and log and all of that?
Because when you get a lot of points, this becomes complex, right?
Sort of, actually.
You have to find out how much each part is, right? You have to split it up. And your formula has one way of doing it for all the points.
See, there are many ways to explain it, but I'll give you one explanation. See, what happens is, if you look at the probability P, going from 0 to probability of something that happened, going from 0 to 1, right? And you look at the log, negative log Pi, P, you will observe something very interesting. What is the negative, what is the log of 0? Anyone?
1.
No. Log of 1 is 0. But what is the log of 0?
Minus infinity?
Come again?
Is it minus infinity?
Minus infinity. Excellent. It is minus infinity. So if log of 0 is minus infinity, what is minus log of 0? Plus infinity, right? So this curve is going to fall like, it's going to go like this. isn't it? So notice that it has that lovely property that when you are grossly wrong, that is, this is a strawberry and you are saying probability is very, very low, the loss would be very high. Not only is the loss high, but more than it being high, look at the slope of it. What is the slope here? Gradient of the loss, the gradient of the loss, which is the slope. Is it very steep here? And so when you do gradient descent, when you do your gradient descent is equal to, this will be really useful. You can take big steps away from those mistakes, right? You can run away from your mistakes faster. On the other hand, if you were doing just this squared or something like this, what you would notice is that your loss function would be more modest. You can convince yourself. It will be something like this. Now, you notice that the slope of this is not as pronounced, right? Especially if you just do this, something like this. Right? So, for example, if your loss is, if you just do 1 minus pi as the loss, then it is like this. Even if you do 1 minus square, it will still be a little bit like this, but you don't get very pronounced gradients. This is more useful. You see, intuitively is far more useful. Now, there are other reasons to do it. I won't go into, but I thought this would be the most intuitive way to explain why you should prefer entropy or surprise as a loss function, and why it has more or less become the de facto go-to approach in classifying the loss. Right? So, all right, enough of a mathematical journey today, and let's take a break. Do you guys have any questions? Are these concepts clear? If not, please ask me. Machine learning is all about understanding loss and then doing gradient descent on the loss. Bhavan.
I think you might have explained this, but this classification for two things.
No. Picking one of many. So, for example, is it a cat, dog, horse, parrot? But regression is about measurables. How heavy is this thing? Right?
Yeah.
That is regression. How many pounds of ice cream should the young entrepreneur buy? And how much is he likely to sell? She is likely to sell on the beach. That is regression. Identifying what is it. So one way to ask classification is classification answers the question, what is it? And regression answers the question, how much is it? Right? So it's the difference between is and much.
Yeah,
measure.
I understood that. I was wondering whether this formula or all those things cover classification between yes and no, or it can be one of many.
No. One of many. But one of many known. Like, for example, you cannot say, here's an animal, but what is it? That's not classification. But you can say, here is my dictionary of animals. Right? Which of these animals is this? That is classification. Yeah, there's a subtle difference between the two. All right, guys, any more questions?
They're going to list the more commonly used loss functions, or is that?
Yeah. I will list it in the portal. That's a very good feedback. I will put some documentation on the most common loss functions. It will be helpful. But a simple rule of thumb is, unless there's a reason to start with MSE, and see, to them you add regularization terms. We haven't covered the topic of regularization, but just the error part of it, the error part, we just start with MSE for regression and negative log likelihood for classification or cross entropy. In neural networks, it's the same thing for classification. Okay. Any other questions, guys?
Asif, could you explain what the gradient as well as like the loss function is next to the graph there?
Oh, who's asking this question?
This is Elisa.
Oh, Elisa, we have covered this in the previous sessions. So I won't cover it because it will be going over ground we have covered, but I'll give you a simple idea. What is a loss? Loss is a measure of how wrong your model is. Simple terms, right? Loss is how wrong is your model? How much does it still have to learn? But on loss function, if you go to some of the earliest sessions, in fact, the second session, you will see a discussion there. Gradient is the slope. So for example, when you are hiking on Mission Peak, the gradient is obvious, isn't it? If you're not careful, you'll come tumbling down. On the other hand, when you are hiking in, let's say, walking along the Alameda Creek behind your house, what's the gradient on that path? What's the slope there? Close to zero.
Zero, yeah.
That's it. So the difference, so that is the notion of gradient. The notion of gradient is exactly that which we use in common language. Gradient, steepness, slope are sort of interchangeable words in common language. In math, it gets a little bit more precise. The slope is for two dimensions, and in higher dimensions, the word slope is replaced by the word gradient. But they both convey the same meaning, steepness. How steep is it? So for example, if you look at this point here, you notice that the function is very steep. You see that where I've made the circle?
Yeah.
But if I look at this point, what is the gradient here then? Close to zero. It's flat.
Yeah.
That is it. That is all there is to gradient from a simple perspective. But starting with that now, you have to build upon. You have to go back and build upon this a little.
So what is the symbol next to that gradient? It looks like, I think it's an alpha.
Oh, you mean this thing?
The one right next to that. Up
Oh,
above.
that is the loss. This is literally the loss, the measure of error. Loss.
Like there's a W, I think, equals W minus.
Oh,
alpha.
this alpha. It
Yeah.
is something called how bigger. So see what happens is that this equation is the gradient descent. What it basically means is if you want to come down a hill, wherever you are, take a small step down. But how big a step you take, it's called the learning rate. The word for that is learning rate. But it basically means how big. Suppose you have a steep slope. A child will take a smaller step, a grown-up will take a bigger step because their legs are longer, right? So this alpha is a measure of that. So the way you want to think about it is that if you're coming down a mountain, the wisdom is in being a centipede or a millipede, taking tiny little steps.
Okay, that makes
You're
sense.
likely to tumble down. Right? So that's your learning rate. All right, guys. So with that, I'll take a break. Let us regroup in 5 minutes.